Hi, I'm Ian Coley, the General Manager of High Performance Computing at AWS. Thanks for joining me today. Back when I joined Amazon in 2017, I had a lot less facial hair, and we had a lot less HPC customers. Why was that? We didn't have high throughput bandwidth, or low latency, like our current C5N with EFA. We didn't have a high performance file system, like FSXa Lustre. We didn't have our AWS Parallel Cluster Orchestration Suite. When I'd meet a customer at SC17, they'd say, I know that Amazon cares about my enterprise workloads, but can AWS really handle real HPC workloads? Now, let's fast forward to where we are today. In 2020, we have customers running their most demanding workloads in AWS, whether it's Formula One racing team running computational fluid dynamics to design their race cars, Halliburton running reservoir simulations to preserve and extend precious energy resources, or Maxar, who is changing the landscape of HPC weather forecasting. No matter the HPC workload, you can run it on AWS. While HPC itself is complex, the end goal is easy to describe. We want the people who use high-performance computing resources on AWS to be the most productive scientists or engineers they can possibly be, as their time is one of the most rare resources on Earth. So our aim is to make sure that they don't waste a minute. If we can make sure that compute is delivered as and when a researcher needs it, we're getting out of their way so they can iterate quickly to the next discovery. Of course, never before in our own lifetimes have we all collectively felt the importance of making sure scientists are as productive as possible as we have now. Fighting COVID-19 has required extensive research across bioinformatics, epidemiology, and molecular modeling. One of the ways the HPC community has come together to address this pandemic is through the COVID-19 HPC Consortium. AWS sponsored 17 HPC Consortium projects, including donations of over $1.5 million in AWS credits and free technical support to help teams in their effort to fight this horrible disease. One example of this collaboration is Novel Tech Sciences. Novel Tech Sciences uses a platform developed by AWS partner Ronin, applying molecular dynamics simulations to identify antiviral compounds that might bind to the SARS-CoV-2 protein. The goal is to create a blend of phytochemicals derived from natural sources that can be used as a therapy and to help prevent the spread of COVID-19. Another is the COVID-19 tree, developed by Iowa State University. Using a variety of evolutionary models together with publicly available genomics datasets, Iowa State researchers constructed the phylogenetic relationship of strains of SARS-CoV-2 and made it available on a public COVID-19 tree website. As the virus mutates as it spreads, this research helps researchers understand how certain variants impact virus hosts. There are also a number of AWS customers who are relying on the performance, scalability, and elasticity of AWS to develop a vaccine. For example, Moderna has invented proprietary technologies and methods that run on AWS to create mRNA constructs that cells recognize as if they were produced in the body. Moderna also runs its drug design studio on AWS's highly scalable compute and storage infrastructure to quickly design mRNA sequences for protein targets. These types of workloads are crucial to developing a viable vaccine. As with Moderna, our customers have important missions. The workloads are complex. They need a lot of different moving parts to work together to get fast answers that can be relied upon. That's why we're here today. Each and every element on this schematic has our own teams of R&D people working to innovate for you, our customers. We have more than 175 services now ranging from things like Nice DCV for remote visualization, all the way to AWS Batch, which companies like Mobileye use for running extremely large-scale simulations of autonomous vehicle trips. They use fleets of hundreds of thousands of cores for that, literally every day. The key components of any HPC architecture are orchestration, compute, networking, storage, and scheduling. AWS is no different. Next, I'd like to walk you through some of the services and products that make it possible to run your most demanding workloads on AWS. First, let's discuss orchestration. AWS Parallel Cluster simplifies deployment and management of HPC clusters. Parallel Cluster uses a simple text file to model and provision all the resources needed for your HPC applications in an automated and secure manner. It also supports multiple instance types and job submission queues, and job schedulers such as AWS Batch and Slurm. This year, AWS Parallel Cluster has been designated as the first Intel Select solution in the cloud. This designation certifies the combination of compute, fabric, memory, storage, and software are used to ensure a high standard of performance and compatibility for HPC. Another exciting development this year is that you can now create multiple job submission queues inside of Parallel Cluster and specify multiple instance types within each queue. This simplifies multi-stage workflows and the ability to run multiple workloads with distinct needs from a single cluster. Next, let's talk about some of the things that make our innovation in compute possible. The AWS Nitro system. Nitro is a collection of cards, chips, and software that remove nearly all the hypervisor functions from the compute path that HPC customers care the most about. Most of the networking functions are on a separate board. We've moved local storage off node, and we let Nitro take care of it. A lot of security features are provided by the Nitro chip that's integrated into the motherboard, continuously monitoring the hardware and firmware. Virtualization resources are offloaded to dedicated boards as well, which makes things really fast, but also minimizes the attack surface. Security really is job zero here at AWS. All this gives us a performance that's indistinguishable from bare metal, and it's allowed our engineers at Amazon EC2 to iterate on an incredible number of new instance types and features. With AWS Nitro cards, we've been able to accelerate the number and types of instances we bring to market. EC2 currently offers almost 400 different instances. Part of customer choice is delivering on your specific workloads needs. We've done that with innovating on our general purpose and burstable workloads, as well as bringing specialized instances to market, like the recently announced M5ZN with the highest clock speed processor in the cloud at 4.5 gigahertz, or the P4d with 400 gigabits per second networking. We have invested in new capabilities over the last year by working with Intel, NVIDIA, and AMD, introducing new instances for accelerated computing and enhanced networking to remove network bottlenecks for high-performance workloads. We plan to continue to bring new instances to market to support virtually every workload and business need. Now let's dive into some of the network-optimized instances that are key to HPC workloads. As most HPC workloads are compute-intensive and network-bound, most customers run their HPC workloads on the C5N. C5N instances use up to 100 gigabits per second of network bandwidth, enabled by Elastic Fabric Adapter, with 33% higher memory footprint compared to C5. The high networking, low latency offered by the C5N are particularly useful for simulations, in-memory caches, data lakes, and other communication-intensive applications. This includes workloads like computational fluid dynamics or finite element analysis. One of the customers taking advantage of C5N capabilities is Amazon Prime Air, where they use these instances to perform the computational fluid dynamics for their drone development. Recently, we announced availability of EC2 UltraClusters on P4d. P4d with EC2 UltraClusters is a powerhouse for training deep learning workflows and other HPC workloads that can benefit from GPU acceleration. EC2 UltraClusters with P4d instances allow you to scale out to over 4,000 GPUs, run on the new NVIDIA A100 GPUs, and are our first instance to support 400 gigabits per second networking, enabled by EFA and NVIDIA GPU Direct with OS bypass. P4d instances provide up to 60% lower cost to train machine learning models, including an average of 2.5 times better performance for deep learning models compared to previous generations P3 and P3DN instances. Researchers, data scientists, and developers can leverage P4d instances to train machine learning models as well as run HPC applications, such as pharmaceutical discovery, seismic analysis, and financial modeling. Unlike on-premises systems, you can access virtually unlimited compute and storage capacity and spin up multi-node machine learning training jobs and tightly coupled HPC applications in minutes without any setup or maintenance costs. Earlier this year, we announced the C6G EC2 instance powered by the ARM-based AWS Graviton2. I'm excited now to tell you about our C6GN instances. Like the C6G, the C6GN offers 40% better price performance over current C5 instances and uses the same ARM-based AWS Graviton2 processors, but has networking speeds up to 100 gigabits per second. As we continue to expand the breadth and depth of Amazon EC2, we want to enable our customers to build their ARM-based applications natively in the cloud. Today, you can optimize price performance for weather forecasting research, fire dynamics simulations, and other open source software applications that can use ARM. For example, Formula One currently uses the C5N to run their CFD workloads to design race cars that can reach speeds over 200 miles an hour. They recently evaluated the new Graviton2-based instances as they offered significant potential to improve the price performance profile of their CFD workloads. Having benchmarked the new Graviton2-based C6G and C6GN instances, they've seen up to 40% lower costs compared to similar workloads run on C5N, and now plan to include Graviton2-based workflows for a range of their CFD simulations. Next to the network. As many HPC applications require high levels of interconnected instance communication, a high-speed network interface is crucial. That brings us to EFA, which is our OS bypass-capable networking offering to support tightly coupled HPC and machine learning frameworks that leverage programming models like MPI and Nickel. EFA can be programmed with the vendor-neutral libfabric API, which is developed by an open consortium of industry and academic participants. Some of the most widely used MPI implementations, such as OpenMPI, Intel MPI, and MVAPitch, have native support for EFA today. Customers like Ineos Team UK used EFA-enabled instances to process thousands of CFD simulations to design their boat for the 2021 America's Cup. What would have taken months for them to do on their on-premises environment only took a single week on AWS. But let's take a deeper dive under the hood of EFA. EFA started with OS bypass features to take the busy work of moving packets out of the kernel and put them into the Nitro card, which owns the slicing and dicing of data and pushes it out over the wire. Building for HPC in a real live cloud as large as AWS is really different. That is what led us to invent EFA and the layer that sits underneath it, the Scalable Reliable Datagram, or SRD for short. At the scale of our cloud data centers, the network fabric quickly becomes complicated. You get a feel for what I mean from the animation on the right. To build a network at a huge scale, you end up having a lot, and I mean a lot of pathways between any 2 points. Other network fabrics, like InfiniBand, see this as a challenge to be managed. Pick a path, the fastest path, and hammer the packets across it, keeping an eye out for performance degradation or packet drops, which can happen quite a lot actually, and be ready to switch to another path if you need to. That makes sense from InfiniBand's point of view, because it maintains that all packets have to arrive in order. And this is pretty much the only way it can achieve that, given its design. The result is that InfiniBand is at the mercy of packet latency, which explains why all my friends in the HPC community always seem to have MPI ping-pong statistics handy. But SRD sees things entirely differently. It looks and sees, wow, there are thousands of possible pathways. That's great news. It's great news because SRD doesn't fixate on the order the packets can arrive. If it's necessary at the application layer, we can assert it later on further up EFA's libfabric stack. So with that constraint-relaxed, SRD takes the whole payload of data that an MPI or Nickel code wants to move and sprays all the packets across all the pathways all at once. It turns out this is incredibly efficient. When you lose the occasional packet on a busy network, or if you have a link that's congested or down or just flipping and flopping, you get what we call head-of-line blocking. All the packets are traveling independently so they don't get stalled in a queue behind a lost packet that's eventually getting detected by a timeout and eventually retransmitted. When we designed EFA and SRD, we ignored synthetic benchmarks and focused on real application codes, because real codes are doing real workloads, and they usually share a lot more than just trivial amounts of data with single tiny packets. As it turns out, this approach worked. Super well, in fact. I'm showing you weather code here because if you're a long time in HPC, you'll know that weather codes are some of the toughest, most demanding workloads to run. They stress everything. And you probably also heard that they're always latency bound. So the data on this graph from the US Navy Research Labs was extremely exciting to see. On this graph, lower is better. So of course we're happy that we had the shortest wall clock times among all the scaling tests. But the best aspect to that red line is that it stays flatter longer than nearly anything in the Navy compared us to. You can see the impact of not having EFA by comparing the red line to the orange line, which is a previous test on our C4 instances before EFA. And this was our first release of EFA. The one you're getting today is built on that success and includes a lot of new features. EFA is pretty important to us, and you can use it without having to modify a single line of code because it lives underneath your MPI stack and just works. And the greater the scale you go to, well, it just keeps working. More scale is more paths. Remember? Next, let's discuss storage. Amazon FSX for Lustre provides a fully managed Lustre file system that allows file-based applications to access hundreds of gigabits per second of data, millions of IOPS, and sub-millisecond latencies. A parallel file system supports the high bandwidth required to handle high throughput and process massive amounts of data and perform operations at low latencies. It does so by storing data across multiple networked servers to facilitate high-performance access through simultaneous coordinated input-output operations. Toyota Research Institute needed a high-performance parallel file system to run their machine learning training sets and chose FSX for Lustre for its integration with AWS services like S3. Toyota cited that FSX for Lustre helped them reduce the time it took to run their object recognition machine learning training time, helping them create features that make their vehicles safer. Whether you're running a dozen nodes or scaling to thousands, FSX for Lustre provides the speed and scalability to maximize performance. And finally, the scheduler. AWS Batch dynamically provisions compute resources based on the volume and requirements of submitted jobs. It will plan, schedule, and execute your batch jobs across resources. There's no batch computing software to install, allowing you to focus on your application and results. Customers like Mobileye use Batch for their autonomous vehicle simulations across hundreds of thousands of cores to improve the accuracy of their vision-based self-driving car and advanced driver assistance systems. Recently, we made running your batch jobs even easier by allowing you to run them on AWS Fargate, a serverless compute engine for containers. When using Fargate or Fargate Spot with Batch, you only need to set up a few concepts in Batch, and you have a complete queue, scheduler, and compute architecture without managing a single piece of compute infrastructure. AWS Batch with Fargate allows you to have a completely serverless architecture for your batch jobs. With Fargate, every job receives the exact amount of CPU and memory that it requests, so there's no wasted resource time or need to wait for EC2 instance launches. So how does serverless batch processing work? The user submits a job, which is effectively an ECS task, to a pre-assigned queue, and Fargate provides a right-sized compute resource to run the job. The batch scheduler submits jobs by priority to Fargate Compute. You can set a cap on the total vCPU run on Fargate, for example, 100. And you can also specify another queue using Fargate Spot to save up to 70%. Once those 100 vCPUs of jobs are running, Batch starts submitting to Fargate Spot. If the job fails, you can specify having Batch automatically retry. You can also specify priorities and dependencies. And that's it. You now have a completely serverless architecture for your batch processing jobs. When analyzing large data sets, transferring the data can be costly and time-consuming. We solve for this with NiceDCV. NiceDCV is an AWS-owned high-performance remote display protocol. DCV stands for Desktop Cloud Visualization, and it provides customers with a secure way to deliver remote desktops and application streaming from any cloud or data center to any device over varying network conditions. Customers across a broad range of HPC workloads use NiceDCV for their remote visualization requirements. The NiceDCV streaming protocol is also utilized by popular AWS services like Amazon AppStream 2.0 and AWS RoboMaker. NiceDCV offers customers enhanced security and cost savings by transferring pixels, not data. NiceDCV specializes on 2D and 3D interactive streaming over Ethernet or Wi-Fi networks, works with any cloud services, including AWS, of course, and any on-premises infrastructure. With the power of NiceDCV, you can seamlessly connect to your running remote session and smoothly interact with it as if you were sitting at the machine itself. You can harness the powerful EC2 or on-prem data center hardware from your personal desktop or laptop and run demanding simulations or analysis from anywhere with an internet connection. One customer using NiceDCV is Volkswagen. Using NiceDCV, more than 1,000 Volkswagen automotive engineers can access CAE applications running in the company's on-premises HPC cluster from home offices or other remote locations. With NiceDCV, Volkswagen engineers had the flexibility to work either on-site or from home, performing the same 3D simulations for automotive design. The company's engineers are taking advantage of improved CAE application performance on NiceDCV to render simulations faster than ever before. Using the new version of NiceDCV, engineers can experience now up to 60 frames per second for CAE applications. Customers across all different types of industries are using AWS, HPC products, and services to run a variety of HPC workloads. I'd like to share how some of our customers are using AWS to run some of their most demanding HPC workloads. Companies like Lyft Level 5 AV run HPC on AWS to improve autonomous vehicle safety through running millions of miles of driving simulations and training their autonomous vehicle models with distributed ML training. Lyft containerized its simulations and ran them on Amazon EKS with EC2 Spot instances and reduced their compute costs by 2/3. Maxar Technologies helped their customers understand the effects weather will have on things such as oil, precious metals, crops, and livestock. Providing this data as soon as possible can help their customers save millions, if not billions. Those of you familiar with weather forecasting know it's an extremely demanding workload that checks all the boxes for HPC: compute-intensive, interconnected, and relying on high-speed connections between nodes. Previously, Maxar's customers relied on weather data generated from NOAA's on-premises supercomputer, which typically takes about 100 minutes to process the data. By using parallel cluster, EFA, and FSXa for Lustre, Maxar was able to reduce the time to process this data down to 30 minutes, less than 1/3 of the time their customers previously relied on through NOAA. Fred Hutch used AWS to run its microbiome research initiative to manipulate microbiomes from over 15,000 biological samples to make therapeutic cancer drugs more effective. Fred Hutch estimates what would have taken them 7 years to do on-premises took them only 7 days to complete on AWS. Another creative use case of HPC on AWS is Fannie Mae. Fannie Mae, who recently migrated from their legacy IBM Symphony grid to an AWS serverless HPC grid and deployed their first financial modeling application to production, ran on 15,000 concurrent Lambda executions. Another company example I'm excited to share is DTN. DTN runs weather prediction models that are used to deliver timely and accurate weather to customers over every continent in the world. The model output is used in analytics engines so that machine learning applications can provide industry-specific and action-based decision support during periods of significant weather. DTN has recently integrated the AWS products and services I previously mentioned: FSXa for Lustre, EFA, Parallel Cluster, and C5N instances. Once DTN started using these services, they were able to save on their compute costs, scale faster, more cost effectively. Whether you're running a CFD workload to design the next fighter jet or running complex weather modeling, AWS enables you to cost-effectively harness the scalability and elasticity of the cloud. No matter the workload, AWS has the products and services you need to run your most complex HPC workloads in the cloud. Thank you.